Today we're going to learn about pMOS and nMOS transistors. You probably know what a switch is. You use it to turn on lights. A switch has a gate, as well as a source and a drain. How you flip the gate determines whether the source and drain are connected, which makes the light turn on or off. A transistor is just another switch that you can turn on or off. You can turn it on by giving it something that it likes to make its source and drain connected. If you give it something it doesn't like, the source and drain will not be connected. We'll discuss two types of transistors, pMOS and nMOS. A pMOS transistor is happy when you give its gate zeros or a low voltage. This makes it connected. It isn't happy when you give its gate a 1 or a high voltage, and its gate becomes disconnected. An nMOS, on the other hand, is happy when you give its gate a 1 or a high voltage, and isn't when you give its gate a low voltage. Formally, both pMOS and nMOS are depicted more like this. And the variable you give it, x, goes here. What about what goes through transistors? This could be either high voltage or low voltage. We get high voltage from power source and zero voltage from ground. In general, pMOS is better at passing high voltages from its source to its drain, and nMOS is better at passing 0 volts. Let's look at a circuit. We have two pMOS and power, which we'll say is logic 1. Remember, pMOS likes zeros. So if A is 1, then nothing goes to the output. If A is 0 and B is 1, then nothing goes to the output. Only when A and B are both 0 will the value 1 make it to the output. Also, a network with only power and pMOS transistors is called a pull-up network. Let's look at another circuit. There's two nMOS transistors, and we have ground, or logic 0, because nMOS works better with ground. Remember that nMOS likes 1s. So if both A and B are 0, then nothing makes it to the output. But if at least one of them is a 1, then 0 makes it to the output. This is called a pull-down network. Let's make a table with the possible values for A and B. For the pull-down network, the output was 0 every time that A and B were not both equal to 0. In the pull-up network, the output was 1 only when both A and B were 0. So what if we take our pull-up network and our pull-down network and then combine the two? Let's go through each row in our table, starting with the first. When A and B are both 0, the value 0 does not make it past the nMOS gates to the output. The value 1 makes it past both of the pMOS transistors through, since pMOS likes zeros, which makes our output for this row a 1. If we go to the next row, A is 0 and B is 1, which means that the high voltage from power makes it past the pMOS transistor for A, but not for B, since the pMOS gate likes zeros and not 1s. The value 0 makes it past the nMOS transistor for B, since B is given a 1 in the table and nMOS likes 1s. Notice how, even though it didn't make it past the nMOS transistor for A, since A is a 0 for this row in the table, the low voltage from ground still made it to the output, which means the output for this row is low voltage, or logic 0. I'm going to step through the remaining rows and see if you can understand each row's output value. Notice how every time only one of either power or ground makes it to the output, and so a value makes it to the output for every row in our table. This is how you make a CMOS gate, and the C stands for complementary. Also, if you look at the values, we just built a NOR gate. That's all for now. Try building a NAND gate on your own, and then compare what you get to a diagram online. Till next time.